Whoa, 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 molecular geometry. We've seen water represented like this, and this, as well as this. So how do we know that water um, has oxygen in the middle and hydrogen on its side, but that it appears that the hydrogen is bent? Notice in all of the models, it is not a straight line, but rather bent. We will learn about this on the next couple of slides. What we already know. Our study of chemical bonds has shown that atoms will gain, lose, or share electrons in order to fulfill the octet rule. For the majority of atoms, this means 8 valence electrons, but with any rule there are exceptions. Hydrogen can be stable with 2, boron with 6, and sulfur and phosphorus can have more than 8. Chemical bonds are a careful balance between attractive and repulsive forces. We know that opposite charges attract and like charges repel. So let's illustrate that. We have our carbon and hydrogen atoms here. The like charges would be the protons within the nucleus of each, and they are repelling each other. The repulsive forces could also include the respective electrons. They're pushing away from each other. But the attractive forces, y'all, the positive and negative charges, they want to be together. So the positive charge of the nucleus would attract the electrons of hydrogen, while the hydrogen nucleus is attracting the negative electrons of carbon. And so again, like it has said, it is a delicate balance. So in order to maintain this balance, electron pairs need to be evenly spaced out around bonded atoms to prevent the bond from breaking. Let's play a little game. Predict the structure. So, rules. The black atom represents the central atom. The white atoms are atoms that will form bonds with the central atom. To form a bond, you must connect the pieces. Also, remember that each of those pieces is surrounded by electrons that are repulsed by each other. Keeping all the knowledge that you have about chemical bonds and repulsion of electrons in mind, try to form the following bonds. So for the first one, we have the central atom bonded to one atom. So these are the pieces, y'all. I'll give y'all a second to try to predict it. Good job! It does just connect to each other. This atom here is as far away from this atom here. Okay, they are evenly spaced out. Those electrons are not too close. It is the farthest it can be. Okay, let's try the next one. Central atom bonded to 2 atoms. So these are our pieces. I'll give you guys a second to predict the structure. Good. This is the structure, y'all. The atoms are located on opposite sides of the central atom. They're as far away from each other as possible. So the central atom bonded to 3 atoms. So we have these pieces. I'll give you guys a second to predict the structure. Cool deal. So the structure is like a triangle. Okay, those 3 pieces are as far away from each other as possible. Central atom bonded to 4 atoms. So these are our 4 pieces. Give you guys a second. How many of y'all actually got this? So it's a square. Well, don't forget, y'all, these molecular structures can also be 3D. So it's not limited to a flat surface. So the best structure that can form with 4 atoms around the central atom is this structure here. Yes, this is pointing up, and this is the top view, y'all. It has that triangle feature that we had before, but we simply added this fourth atom on top of it. Okay, let's learn more about these names of the structure and how we can determine them. Molecules of different substances have diverse shapes. Atoms attach to one another in various geometric arrangements, as seen here, y'all. Some of the shapes that we are going to cover would be linear, trigonal planar, bent, tetrahedral, and trigonal pyramidal, trigonal bipyramidal, and octahedral. And there are a couple others too. The overall molecular shape of a molecule is determined by its bond angles in 3 dimensions. I want you guys to write that one down. I want you guys to write down overall molecular shape is determined by its bond angles in 3 dimensions. The shape of a molecule is important for its physical and chemical properties. Be sure to note that as well. The shape of a molecule is important for its physical and chemical properties. We have something called the Vesper theory. Vesper stands for valence shell electron pair repulsion. It predicts the molecular shape of a bonded molecule. Electron pairs on central atom, bonding and non-bonding electron pairs, repel one another, and as a result, the electron pairs remain as far apart as possible from each other to minimize the repulsion. So to illustrate this, y'all, I'm going to look at the water molecule. So this is the Lewis diagram of the water molecule with the shape drawn in with it. Now the different parts. So these lines are called the bonded pairs, or they're the shared electron pairs. Then these two dots that we see on top of oxygen would be the lone pairs, or the non-bonding or unshared electron pairs. So these electrons try to be as far away from each other as possible, forming this shape here that you guys see. So in this picture here, we have the lone pairs being represented by these purple, and I like to call them the Mickey Mouse ears. Hi guys! No, that sounds a little more like the gingerbread man, but you know, you get the point. And then the shared pairs would be the bonds we see here. So bonded electrons. Shared. Continuing on with this, y'all, lone pairs and bonded pairs. The repulsion of lone pair electrons only on the central atom is greater than the repulsion of bond pair electrons. But why? So this is an illustration of a bonded pair. The electrons are being shared between X and H. And again, this is the model for it. We see that a bonding pair is shared between two nuclei, and the electrons can be close to either nucleus. They are relatively confined between the two nuclei, so again, not much room, y'all, to move about. Could be close to X, could be close to H, but again, this is its confined area, not much space. But a lone pair is localized only to one nucleus. So the two electrons can't move about in this entire region here. Okay, so the lone pairs electrons can move within this space. The model version of the lone pair, again, the Mickey Mouse ears, represents this big area, y'all. So it's illustrated there. Now, let's talk about the strength of these repulsion. The greatest strength would be lone pair to lone pair. So again, these guys, two of them would be pushing each other away the strongest, strong repulsion. Then the next one would be between a lone pair and a bonded pair. Remember, the bonded pair is very, very, very localized, so it doesn't have a lot of room, doesn't repel as much. And last but not least, y'all, the bond pair to bond pair, least repulsion. Applying the Vesper theory. Step 1. We must draw the Lewis-Dot diagram of each of the elements in the molecule, with the least electronegative in the center. Why is that? So again, the least electronegative element has the tendency to let go of its electrons. They share them, okay? Whereas the one that has high electronegativity, those nucleus, again, wants to attract those shared electrons closer to it. So it would be considered a terminal atom. So the least electronegative in the center, to recap. Step 2, determine the number of bonded and lone pair electrons on the central atom. And step 3, arrange the atoms around the central atom so electrons are as far away from each other as possible. So step 2 is the crucial step that determines the shape. And I'm going to be recapping this throughout the lecture. Okay, so step 2, determine the number of bonded and lone pair electrons on the central atom. Okay, so that is the crucial step. Linear. So it's two atoms attached to a center atom. And then it could also be just between two atoms as well. It has 0 unshared pairs or lone pairs on the central atom. Like I said in step 2, the central atom, we need to determine the number of bonded and unshared pairs or lone pairs. And that actually determines the shape. The bond angle is 180 degrees. And our example is beryllium difluoride. And so to draw the structure, we draw it like so. And I'm going to note the bond angle. You guys don't have to. I'm going to do it in a different color to show you guys it's not part of the shape. So it's 180. Bent. So bent is two atoms attached to the center atom, similar to linear, but it has two lone pairs on the central atom. The bond angle is 104.5 degrees. And our example would be water. So to draw this out, y'all, again, I'm going to draw it like so. And then I'm going to note the angle here. Trigonal planar. 3 atoms attached to the center atom. 0 lone pairs on the central atom. The bond angle is 120 degrees. And our example is aluminum fluoride. So how do we draw it? Again, I am going to draw it like so. Similar to a triangle, y'all. The bond angle, I'm going to be labeling it. Again, 120 degrees. Trigonal pyramidal. 3 atoms attached to the center atom. We have 1 lone pair on the central atom. The bond angle is 107 degrees. And our example is ammonia. So I'm going to draw it like so, a short leg, longer leg, and another short leg to represent this kind of like a tripod. Similar to how we see it rotating here, is all pointing down. And then the angle, and I'm going to make it a sharp angle right here, is again 107 degrees. Tetrahedral. 4 atoms attached to the center atom. There's 0 lone pairs on the central atom. The bond angle is 109.5 degrees. And our example is methane. So how do we draw it? I draw the central, and I add the one on top, add again the legs here, and a short leg pointing back. The angle would be 109.5 degrees. So here we have the seesaw. The 4 atoms are attached to the central atom. There's considered to be 1 lone pair on the central atom. And it has 2 bond angles, y'all. 9 degrees and 120. So the 120 would be between these guys here and the 90 degrees, again, over here. So our example is sulfur tetrafluoride. And how I'm going to draw it, I'm going to draw it like so, straight line, and then one leg going out and a short leg in the back to represent this one right here. And we have the bond angles. I'm going to label it appropriately too. So we have 90 degrees. And then over here between these guys would be the 120. Trigonal bipyramidal. So we have 5 atoms attached to the center atom. And the easiest way we can identify this one is that it forms a trigonal planar with a top and a bottom. And what do I mean by that? I'm going to illustrate it for you. That right here is the top and the bottom. And if we are to focus here, y'all, this forms a triangle. So that's the trigonal part. Bi is the top and bottom too, right? So the next thing we should note is that there's no lone pairs on the central atom. So the bond angle, y'all, again, equatorial, 120, and that is the one that looks like a triangle. And the axial is 90 degrees. Our example would be phosphorus pentafluoride. So how do I draw the structure? Again, the central atom, a top and a bottom. And I'm going to try to draw my trigonal planar here. Okay, so now the angles time. So the angle between the trigonal would be 120, and then from the top to here would be the 90 degrees. Octahedral. 6 atoms attached to the center atom, 0 lone pairs on the central atom. The bond angle would be 90 degrees. And our example is sulfur hexafluoride. So how do I draw it? Again, we have a top and a bottom. But instead of forming a triangle this time around, we're going to try to form a square. I'm going to show you guys a square here. If we concentrate, it forms a square there. So I'm going to draw that square in my picture. So the angle, again, I'm going to color in red, is 90 degrees. Here's a quick reference for all the different shapes, given the number of atoms attached and the bonded or lone pairs. So atoms would be represented by the X here. So these are 2 atoms attached, 0 lone pairs. We have 1 lone pair, and then the 2 atoms attached, etc. Okay, so this is a good overview. It also represents the shape as well, drawn in this case with something called the wedge and the dash. So you guys will see this quite a bit if you guys take organic chemistry. And these wedges, y'all, they represent going out of the paper. So that means it's coming out at us and it's about to hit our face. So this X right here is popping out at us, okay? And then over here, this lone pair is popping out at us. The dashes, y'all, the dashes represents going into the paper. So it's pointing away from us. It's the farthest one away from us. Okay, so again, I'm going to illustrate that here. That is the dash. It means it's pointing away, going into the paper, away from our face. So we shouldn't be too scared at this one. It doesn't pop out at us like the wedges do, but it points towards the paper, away from it, if we're trying to visualize all of these shapes in 3D. Predict the shape of CO2. So the first thing we should do is always to draw the Lewis dot diagram. And that's what I have right here. So I take a look at the central atom and see how many atoms are attached to it. So I'm going to be analyzing that. I see that I have 2 attached to the center, no lone pairs. This means I can look at my notes and I see that the only one that fits the description would be linear. So linear is right. It is a straight line. This is linear. Okay, bond angle would be 180 degrees. Okay, the next one, y'all, HCN. So that's the Lewis dot diagram. Again, I take a look at the central atom and I see that there are 2 atoms attached to it, no lone pairs. So this would be linear as well. And I can see that it does form a straight line. Let's look at the model. Boom, we are right, a straight line there. Predict the shape of methane, ammonia, and water. So for methane, y'all, it is 1 atom with 4 atoms attached to the center. So if we take a look at our notes, 4 atoms bonded to a central atom with no lone pairs would be considered a tetrahedral shape. Okay, this is the 3D model, and you can also draw it as this as well. Next, we have ammonia. Ammonia is nitrogen in the center with 3 hydrogen atoms attached to it, as well as 1 lone pair. And if we take a look at this, y'all, its shape should be trigonal pyramidal. Okay, trigonal pyramidal. This here has this lone pair pushing the hydrogen down, just like we see it here. And we don't have to draw the lone pair shown. We can simply draw it. If you want to draw it with the wedges and dashes, like so, with the 2 dots there, and that's fine. Last but not least, we have water. So water is O with 2 H's attached to it and 2 lone pairs attached to the central atom. We take a look at our notes and the shape is considered to be bent. Okay, bent. And we have the 3D models and the 3D models using H and O's. Now I want you guys to try to determine the shape, y'all, given the molecular formula here. Phosphorus trichloride, sulfur hexachloride, and a nitrite ion. Let's make sure that you guys have already done it. This is the solution to PCl3. So phosphorus trichloride. First, I'm going to draw the Lewis structure. Now I'm going to be using the shortcut method. But I'm going to be sure to line up my valence electrons so that it points to create a bond so I don't have to rewrite it, y'all. So connect the dot, connect the dot, connect the dot. Now let's analyze. We take a look at the central atom and label how many atoms is attached to the central atom. And so we have 3 atoms attached to the center, and we have 1 lone pair. This drastically changes the shape from trigonal planar to trigonal pyramidal. So the shape is trigonal pyramidal. So I can draw the shape with the P's and the CLs like so, or I can draw it with the sphere, y'all. So again, I know CL, these legs are kind of like the tripods. Okay, there we have it. Okay, I'm going to work out sulfur hexachloride. So if there are more than 4 atoms attached to the central atom, as in this case, we can't use the shortcut method of the Lewis dot diagram. We have to determine the total valence electrons and split them up. So let's do that first. I'm going to count the total valence electrons for my molecule. Sulfur has 6 valence electrons, chloride has 7 valence electrons, and there are 6 of them, so I'm multiplying it. So I'm going to make sure I do that one first. 7 times 6 is 42, plus 6 gets me 48 total valence electrons. But to make my drawing easier, I'm going to divide that by 2 to put everything in pairs. So I have 24 pairs of electrons. Okay, so now let's draw it out. I have S, and then now I'm going to place my chlorine atoms around S. So 1, 2, 3, 4, 5, and 6. Then I'm going to count down by placing the bonds to them. So 1, 2, 3, 4, 5, 6. Again, I want to get 24 pairs. I have 6 so far. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I know all of my valence electrons has been used up, and this is my Lewis dot diagram. Now, let's analyze. I have my central atom, and I have 6 atoms attached to it, but 0 lone pairs. So if I take a look at this, y'all, this gives me the shape of octahedral. Okay, octahedral, and this shape would look something like this. Again, that's supposed to be a straight line. The square with the top and bottom there. And I'm gonna draw it, if you guys really want to, the plane the wedge. Okay, there we have it. Okay, so we have nitrite ion. This is unique because it has a negative charge. We haven't seen anything like this before in our examples, so anytime you see a unique situation, always use the default method of the long way of drawing the Lewis dot diagram. We have to determine the total number of valence electrons. We have nitrogen having 5. Oxygen has 6 valence electrons times 2. So we do that first, y'all. 6 times 2 is 12, plus the 5 gets us 17. This negative charge forces us to say it gained an electron. That's what the negative means. Gain an electron, so we add 1 more for the total of 18 valence electrons. I divide it by 2 to get 9 pairs of electrons in my diagram. So now let's draw it. Nitrogen is in the middle, and I have oxygen on either side. So now I'm going to be using up the pairs. I draw a line, so that's 2 pairs. Oxygen has 2 lone pairs in its normal Lewis dot diagram. So I'm going to draw those 2 lone pairs, y'all. So 3, 4, 5, 6. So I have used up 6 so far. I need to place 3 more pairs. So now I'm going to take a look at nitrogen. Nitrogen's normal Lewis dot diagram has it having 1 lone pair. So I'm going to be placing one of those lone pairs here. So now I'm at 2. So let's see, y'all. I need to find or have the negative charge be present as well. So I'm going to make nitrogen. It has 1, 2, 3, 4, 5, 6 valence electrons around it. It just needs 2 more. This makes it have 8. So nitrogen is stable. Oxygen here is stable. And I have 1 more left over. So with that said, I'm actually going to be adding this last one just to make this oxygen here stable. So now it has 1, 2, 3, 4, 5, 6, 7, 8. But since it has an extra electron lone pair, it breaks its rule a little and it gets a negative charge. Okay, it has 1 extra electron on it, where it normally wouldn't, because again, it has only 2 unshared electron and 2 lone pairs. So I'm adding that negative charge there. All of them are stable. We now analyze the central atom. It has 2 atoms, and 1 lone pair. So based on that, we have the shape bent. So I'm going to draw that out. So again, bent, and it has a double bond, so I'm going to draw a double bond. And over here, if I want to draw the other one, I can. Lone pair, and double bond O, O. And there you have it, y'all. This is bent.